Welcome to CS 1033 Programming Fundamentals module. We will discuss the lecture on recursion in programming. The contents that I will cover is an introduction to recursion, and then we will go through several examples of recursive functions, specifically functions where you are familiar with the computation, computing factorials, computing the greatest common divisor, and computing the nth power. Then we'll discuss recursion versus iteration. Also, we'll look at tail recursion, which allows us to do our programming work more efficiently. Finally, we will look at several recursive problems which are used as classic problems to discuss use of recursion for problem solving. Okay, so we'll discuss checking strings for palindromes, as well as the classic problem of towers of Hanoi. Now, recursion is essentially a problem solving method. Okay, and it is used, it has been used in computer science for a long time. It has a history of very successful use, and it is particularly useful because it makes analysis of a problem quite simpler. So the idea of recursion is that a solution to a problem is based on solving a smaller instance of the same problem. Okay, so let me repeat it again. So you have a problem to solve. So the solution to that problem is based on solving a similar but a smaller version of the problem. So this argument can be applied repeatedly, which is what we call the recursion. So when you formulate a problem in this manner, where a problem can be solved using a smaller version of the same problem, the part of the problem or the instance of the problem that is similar to the originally stated problem is what we call the recursive case. Okay, so there are two cases actually. So one is this recursive case, which you will apply, and when you use the same argument. Okay, so we have the problem, solving that is dependent on solving a smaller version of the same problem, and you take that one and then use the same argument. So increasingly you will get smaller and smaller and smaller problems. Okay, finally you will get to a problem which can be directly, or we call it trivially, solved. Okay, so that is called the base case. So two cases: the recursive case, which is the generalized version of the smaller instance of the problem, and the base case, which is the trivially solvable instance of the problem. So as you increasingly make it a smaller and smaller problem. The recursive steps, okay, are applied as a chain, and at the base case, this repeated application of the smaller problem as part of solving the overall problem stops, and it is called and therefore it is called the terminating case. Okay. So base case, another name is terminating case. Now let's look at the very familiar computation of a factorial. Okay, so we have a straightforward equation for the computation of the factorial. So factorial of n can be computed by multiplying n with the factorial of n minus 1. Okay, so you can see here, this is a smaller version of the original problem. Original problem is compute the factorial of n. This is a smaller version, compute the factorial of n minus 1. Of course, we have the condition, this equation is valid for all n greater than 0. Now, what would be the base case or the terminating case? Terminating case is when you keep on reducing the value you need to compute the factorial of, ultimately you will get 0. So we know by definition factorial of 0 to be 1. Okay, so that would be our base case. So we should develop an algorithm that takes these two cases, the recursive case given here and the terminating or the base case given here, and put them together into an algorithm to solve the problem of computing the factorial. So as you can clearly see, we are moving from an original problem to the same problem but of a lower complexity, because the value on which you need to compute the factorial keeps getting smaller and smaller. So this is the idea. This reduction should ultimately end up with the base case. So the implementation of recursion in programming, you do that with function calls. Okay, where the argument to the function gets modified. Okay, for example, now let's say the factorial function has the name fact. Okay, so we can call that function originally with an argument or a parameter called n. Then within that, we can call the same function. So the function will call itself. Okay, function will call itself with the parameter n minus 1. So one thing we need to remember is, generally this type of recursive calls are considered to be computationally expensive. So why is it computationally expensive? So you already have some knowledge on how a computer works. So when the computer executes a program, it basically has the instructions that it executes and the data it manipulates, and the microprocessor or the CPU has a program counter which maintains the address of the current program it is executing. So whenever it executes, whenever it gives an instruction to be executed, it will get incremented to the next instruction. And the CPU also has several registers which contain data, maybe partially computed results, maybe input values, and also index values that get incremented. So like that, there are several registers which contain data. So when you call a function, this current state of the CPU need to be saved. So all the state information like the program counter, registers, and things like that will get stored into an area of memory called the stack. Okay, so so this work is additional work. It's like housekeeping work that you need to do to keep the program running. This storing of um, state, which we call a context. Okay, so after storing that, the program counter, the instruction pointed by the program counter will get executed, and the registers will get loaded with data. Certain other registers will get loaded with input data, and some others with computer data, like that. And this changing of the state is what we call in the, for example, in operating systems as a context switch. Now, all this is additional work, okay, which requires the computer to do this housekeeping work, which is not related to actually solving the problem. To solve the problem, we are executing an algorithm. So this is additional work. So that is why we call it as computationally expensive operation. Now, the execution or the recursive execution of a function will essentially force the CPU to do this, because whenever you call a function, this is the standard set of activities that happen. Okay, take a copy of the registers, put them in the stack, and then proceed to call the function with the new set of parameters. So every time you call fact with a parameter, this will happen. So let's say you started with fact and the parameter n. So now when it gets executed and within that you call fact with n minus 1, you basically stop whatever you are doing, store the state to the stack, and execute that function. Okay, so this way it will keep on creating a stack of function calls, right? So only later, when you have reached the base case, the terminating case, you will start to return from this function calls. Then whatever you have stored in the stack will get restored to the CPU. Again, additional work. Okay, so that is why I want to again reiterate, using recursion is a lot of computational work, which essentially slow down your computer. Okay, but having said that, recursion is a very elegant way to solve problems. Now let's look at the Python code for the factorial function. So here's the equation. So when you want to compute the factorial of n, here I have the base case. Okay, base case is when n equals 0, the answer is 1. And for any other case where n is greater than 0, you can compute the factorial by multiplying n with the factorial of the number less than 1. Okay, so this is the factorial of n minus 1. So implementing this in code, here I have defined a function called fact, passing the parameter num, and so I have a if else conditional structure to do the computation. So here I will check the base case. If the parameter is equal to 0, I will take the result as 1 and I will return the result. Okay, I'll return the result. Otherwise, I will call this instruction, okay, which is the same as what I have here in the equation. So num multiplied by computing the factorial of num minus 1. So I'm now passing num minus 1 as the parameter. Okay, and when I get the result of this call, I will multiply that result with num and then return that as the result. Okay, so this basically the recursive implementation of factorial function using recursion. Okay, straightforward. You can see the equation to code mapping is quite straightforward and direct. You can see it actually visually. Let's look at how the execution happens based on what we discussed about the recursive call of function. So this graph structure is a visual representation that will help you to understand it, where we will be calling the factorial function with different parameters. So, okay, here's the start. Okay, here's the start. We initially call with factorial of n. Then, if n is greater than 0, it will get rewritten as n multiplied by n minus 1, the factorial of n minus 1. Now, factorial of n minus 1 in the next step gets rewritten as n minus 1 into factorial of n minus 2, so on and so forth. And at some point, because this is a reduction by 1 at each stage, it will say 2. Then if this is 2, this would be the factorial of 2 minus 1. Okay. Oh, sorry. This would be the factorial of n minus so yeah, so let me type it here so it will be clear to you. So this would be n minus n minus 1. Okay, so that would result in the factorial of that. Yeah, the factorial of that. So essentially, that would be the factorial of 1. And factorial of 1 would be 1 into the factorial of 0. Okay, which is the terminal case. Okay, we have already decided on that, the terminal case. So now we can replace that with the answer 1. So that is what you are seeing here. Okay, so when we get to that point, we will put the answer 1. Okay, so 1 times 1 is 1, and that is the answer which is now returned here. And then this answer is 1. 1 times 2 is the answer, which is again 2, that gets returned here. Okay, and then 3 times 2, 6 is the answer that gets returned here. So it goes on like that. So this is where n is equal to 5. So you can see it will gradually increase to the original problem. This is the original problem, giving us the result. Okay, at every stage, we only do a straightforward multiplication only. These are all multiplication of two integers. Okay, so because this value is returned to us from the previous function call as a result. So the solution, as you can see, is getting built up step by step from bottom to top. So let's look at another example. Here we want to compute the greatest common divisor. Okay, so as per the definition, greatest common divisor can be computed using the Euclidean algorithm. So let's look at the two cases. So the base case, the terminating case is when the second value, okay, so always remember when we pass on the values for the Euclidean algorithm, we have the x value greater than y, okay, x value greater than y. So the value that would reach 0 first would be the second value of the value pair. So we are checking if that value is equal to 0, then the result is the first value. Okay. So the greatest common divisor between two values where the second value is 0 and of course the first value should be non-zero would be the first value. And for any other case, this is the recursive scenario. This is the recursive case. The greatest common divisor is the second value from the previous call and the remainder of the pair xy. Okay, so this is how you would create the base case and the recursive case. Let's look at the Python code to see how this gets implemented. Okay, so here we are defining a function GCD, okay, and we pass two parameters x and y. Okay, so when we call it, we should be mindful to call with x greater than y. So we'll first check for the base case. Okay, if so, this is the checking for the base case. If y is equal to 0, simply return x as the result, as noted here. Otherwise, we go into the recursive case. Okay, so we will store the y value temporarily into a temporary variable called TMP. Okay, and then compute a new y value by dividing x by y. Okay, dividing x by y and taking the remainder. So so normal division is that symbol, and we have the percentage symbol for the modulo division, where we will get the remainder after dividing by y. Okay, and then we put the original y value which we have stored into a temporary variable to be the new x value. Okay, and then we call the GCD function with the new x value. So this new x value is the previous y value as shown here, and the new y value, which is the remainder of the original x divided by the original y. Okay. So once you have the problem defined as a base case, here's the base case, and a recursive case, here the recursive case, then implementing it as an algorithm which a computer can process is rather straightforward, as shown here in the Python code. Another example, so we had 3 examples. So this is the third example, computing the nth power. Okay, so let's review the Python code to compute in the nth power. Here we have the mathematical representation of the base case and the recursive case. So if you consider the base case, when n equals to 0, okay, the power of any value raised to the power of 0 is 1. Okay, so that's the base case. And for any other value of n greater than 0, the computation would be x multiplied by x raised to the power of n minus 1. Okay, because as you know, when the base is common, the exponents get added. So this exponent here is 1 and this one is n minus 1. So same base. So you can reduce this by adding the two exponents, 1 plus n minus 1, which would result in n. Okay, so yeah, so when n is greater than 0, that would be the recursive case. So let's look at the computing this using Python. So the mapping of the solutions is our solution, a recursive solution to an algorithm implemented in Python. So I'm defining a function called n power, which gets two values given to it. So mind you, I'm not doing certain error checks here. For example, the n should be a positive value or a 0, can't be a negative value, things like that. So, so in an actual program, there'll be additional code before calling the method, the calling this function here with certain parameters, okay, parameter values. But here we are looking at the algorithm. So here's the implementation using if then else structure. So base case, if n is equal to 0, return 1, else call the function, do a recursive call on the function with the value being the same, x, and the value to which it should be raised, the power to be n minus 1. And when that result is returned to you, multiply that with the x value and return the full value as your result, as shown here in the recursive case. Okay. Now, the implementation we have just seen followed the standard scheme. Okay, consider the base case, consider the recursive case. Okay, so you can see it is a standard implementation. Okay, standard implementation. So let's look at a further improvement to the algorithm. Okay, now if you visualize the recursive tree structure, which is the same as what we have had for the computation of factorial, no, there are n number of recursive function calls. Okay. Now that means no, it's like a, so if you really visualize, it was like a tree with no, just branching out and going down no, stage by stage. So the number of calls here would be n, no, because at each step the n gets reduced by 1. But we can use some additional knowledge we have to improve the situation. Okay. Now, if n is an even number, which can be nicely divided by 2, then we can write x to the power n as x to the power of n divided by 2 raised to the power of 2. Because as you know, exponentiation of an exponentiation is the multiplication of the exponents. So here it would be n divided by 2 multiplied by 2, which would be n. Okay. So with this knowledge, we can implement the recursive algorithm even more efficiently. Okay. So let's look at the Python code for that improved implementation. Mind you, the base case doesn't get changed. The recursive case doesn't get changed. It is only this additional knowledge we have. If n is an even number, which is divisible by 2, then the computation of n power can be done in that different computation of n by 2 exponentiate by 2 or squaring of that. So here's our equation in this case. So this is actually the recursive case, what you can do in the recursive case. So when n is odd, we will take an x out. Okay. When n is odd, we take an x out, and then the n value is divisible by 2. Okay. And when n is even, we can directly divide it by 2. Okay. It's divisible. Okay. So this n divided by 2 is the integer division. Now let's look at the Python code implementation. You should type this into your own Python environment and test. So you can see I have defined a function n power fast, okay, to show that now this is the improved version. I will pass a parameter x and another parameter n. So what I want is to compute the value of x raised to the power of n. Now, first of all, I will apply the base case. Okay. So the base case hasn't changed. If n equals to 0, that means the power to which it should be raised, which the base should be raised is 0, you return 1, because anything raised to 0, the result is 1. Then I have the recursive case. Now recursive case comes in 2 cases. Okay. When n is an even value and when n is an odd value. So here I would divide n by 2 and get the remainder. If the remainder is equal to 0, that means it is the even case, because it got divided by 2 nicely. In that case, I will compute a value by calling the same recursive function with x as the base and n by 2 as the exponent. Okay, because we can divide n by 2 with no remainder. Okay, and this particular value, so the HP is this value. Okay, so I need to square this value, multiply by itself to get x raised to the power n. So this HP value, okay, so that's half the power value is multiplied by itself, and that is the full value which gets returned. Similarly, the other case, so if it is not equal to 0, that means I have to consider the odd case. So in the odd case, I will again compute the x raised to the power of n by 2. Okay, n by 2. So it doesn't matter that n is not divisible cleanly, but no, you get whatever the full when you do the full division, the full value. And now you can see I have to get the half value multiplied by itself because of the squaring, and then multiply that with x. So that's what I'm doing here. HP is multiplied by itself, and then that result is multiplied by x. Okay. So this is the implementation of n power, which will run faster now. Okay, which will run faster because earlier you would call the n value recursively with n reducing in each call. In each call, n gets reduced by just 1. Okay, you can see that here. N gets reduced linearly just by 1. Okay, but here much faster. N gets reduced every time by division. Okay, so this would get to the base case much faster. Okay, much faster. So you should implement this, give a bit of a large value set, and see how fast it executes. Now this is a good time to actually talk about iteration versus recursion. Now all these problems that we looked at, which naturally lends itself to a recursive solution, can also be solved without using recursion and only using simple iteration. So this approach looks very attractive because, as we discussed, recursion is computationally expensive because of that context switch that you have to do, where you have to store the current state of the CPU in the stack and keep on calling the functions recursively, and then whenever the functions finally get to base case and return, you have to return the results, and at that point again, the whatever that was stored in the stack gets copied back onto the CPU. So quite expensive. So how do we move from the recursive algorithm to the iterative algorithm? Okay. So the trick or the method is to use an index to figure out whether we have called the function repeatedly with the change parameters. Okay. Now, when you use recursion, sorry, when you use recursion, the solution kind of naturally build up, because you have a problem, you make the problem smaller. You are not looking at a solution actually. You have a problem, you make the problem smaller. Okay, and then you take that problem, make it smaller, and then take that one, make it smaller. So recursively you make the problem smaller and smaller and smaller, and at some point you get to a problem which is trivially solvable, which we call the base case, and then you work yourself up by creating those partial results. Okay, so when you use recursion, you don't actually need to create a computable solution. Okay, so this is quite interesting outcome. Okay, you only get to the base case. But if you are using iteration, that won't work. You have to formulate a solution. Okay, right? So that's a important difference. That's why actually programmers prefer recursion. Now, so as I mentioned earlier, calling the recursive function will generate this call stack at runtime, which is equal to number of calls, and so it's computationally inefficient way to do things. So um, so that's why we are looking at replacing recursion with iteration to get this efficiencies. But it must be always remembered that the recursive algorithm is always more elegant. Elegant means the solution that you get from a recursive approach is much easier to understand, much simpler to explain, and even easier to code. Okay, so so those are very important aspects um, in certain instances. Okay, right. So as an example, let's look at the implementation of factorial function using iteration rather than recursion with Python. So this is the iterative approach of computing the factorial of n. So we start by saying the answer is 1. So we have a temporary variable and we give the value 1, and then I would do a repeated computation going from 1 to n plus 1, okay, and compute the answer with repeated multiplication. So as you know, this is how you normally compute factorial. Factorial of n is 1 times, 2 times, 3 times, 4 times, the multiplication up to the n value. So so that's what I'm doing here. Okay. So yeah, so because factorial computation is a simple equation, so there is no difficulty actually understanding what you are doing here. But there are some other scenarios where the solution is not so clean and easy to understand. Let's look at the computation of nth power. Again, this is the iterative version of exponentiating x by n. So this exponentiating x by n. So we know that it's done by repeated multiplication, uh, and so the answer is again set to 1, and then we start repeated multiplication with x, okay, and return that as the answer. Okay, so you can see, because these are simple functions, the implementation doesn't look any complex. You can still understand, but that happens only for this kind of simple problems. Now let's look at a bit more involved algorithm. Okay, the computation being done at a faster rate. So raise a to the power of n, okay, and we are going to use iteration, and so here's the algorithm. Okay, so if so the exponent, if it is divisible by when you divide by 2, if there's a remainder, which means it is not divisible, So you multiply your current answer with the number value which you are computing as you go on, that you initialize to A at the beginning. Otherwise, you just multiply the number. So this is like the x squared. This particular computation, and here so yeah, let me repeat again. So if the k value is even, then when you divide by 2, remainder would be 0. So the result is directly multiplication of the number by itself. Okay. So the half value multiplied by half value. If the k value is an odd value, which means when you divide by 2, there is a remainder, before coming here, the answer value is computed as the previous answer multiplied by num. Okay. And then, because if you recall that our algorithm, every time we would divide by 2 when we are going to the next iteration. Okay, so in the fast scheme we divide by 2. In the slow scheme we subtract 1. Okay, so it was n minus 1 in the standard scheme, fast scheme, n divided by 2, and we return the computed value. Okay, so so this is the faster version. So you should write the code to your Python environment and test it, and you can see this algorithm is not intuitively clear like the earlier solution. So this is the problem. Okay, so as your problem gets more and more complicated, or your solution gets more and more complicated. So here actually the problem didn't get any more complicated. It was the same original problem of computing the in power, but now what has happened here is we have a bit more complex solution, the faster version, and now it is not clear how the solution works, because in the earlier scenario of using recursion, the faster version is also clear what you are doing. The solution is intuitively, you can understand that. So always remember this trade-off when you are moving from recursive solutions to iterative solutions. However, to get a kind of middle ground, you can still have recursive execution, but with a slight not slight actually, you can improve the runtime efficiency by using what is called tail recursion. Okay, so in tail recursion, all the recursive calls are what we call tail calls. That means they don't get stacked. Okay, so so when you are calling the recursion, the recursive computation will happen, and then a solution will be returned, so that the calling of the stack operations by the CPU does not happen. So you have to actually very specifically create the algorithm for this. tail recursion does not happen naturally when you solve the problem using a base case and a recursion case. Right. So this um, issue of efficiency is always there because normally in a microprocessor, when you call a function, it is executed using a instruction like JSR, which stands for jump to subroutine. Jump to subroutine, which will automatically initiate that context switch of storing the state of the CPU in a stack. So the tail recursion would allow the execution of these subroutines not using a JSR. Okay, so not a jump to subroutine, but what are called jump instructions. Normally the mnemonic is JMP, jump. Okay, or depending on the microprocessor, it will change. So this is the difference. Okay, so if you use conventional recursion, this CPU will use subroutine calls. If you use tail recursion, CPU will use jump instructions. So make a careful note of the two different machine instructions that are used in the execution. Let me repeat again. Conventional recursion will be implemented using subroutine calls. Okay. In tail recursion, it will get implemented using jump instructions. So jump instructions does not require the storing of the state to a stack. So there is no context switch. So it is quite efficient. Here I have a Python code which demonstrate what is happening here. So as noted here, the Python code will run recursively, but will read the base case without having to do any other computations. Okay, so let's quickly look at the example here. Actually, suppose you ask to compute the greatest common divisor of 10 and 8. Okay, so this is the function definition. You call with x and y, and so what get passed is 10 and 8. So yeah, 8 is not equal to 0, so therefore it will come here and it will call the same function GCD with now this particular parameter coming as the first parameter. Okay, so it will be 8, and the second parameter is divided by 2, and the remainder put there. So okay, so 10 divided by 8, remainder is 2. Okay, because 8 times 1 plus 2, okay, is 10. And then when you check the second parameter y, it is not equal to 0. So you again call GCD, and here 2 becomes the first one, and then 8 divided by 2, it cleanly divides, remainder is 0. So that is what that goes here. And when that call comes here, because y is now equal to 0, it will immediately return 2. That means the first parameter value that came as the result. Okay, so x gets returned as a result. Okay, so then you can see immediately they keep returning. There are no other computations happening. Just return, 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 return. Um, so therefore, um, there is no requirement to implement this using subroutine. You can implement this using jump instructions. So of course the final answer is 2. So let me quickly go back to the original discussion we had on the greatest common divisor to show you what was our problem here. Okay, so in the original implementation we had the computations happening here. So if you are doing computations here, you have to do a swap of the state to the stack. Okay, because that is required whenever you do the recursive calls. But in this particular tail recursion that we just discussed, you can see we are not doing any such computations here. Okay, so that allows for the compiler, which compile this code, this program code, to create a program that runs in the processor without using JSR, the subroutine calls, but only using JMPs, the jump instructions. Okay, so now we have actually completed our discussion on the introduction to recursion, how it helps us to solve problems, and we looked at 3 very easy to understand mathematical functions and their implementation using recursion, and then we looked at certain tweaks we can do to improve the performance, and also we discussed this issue of computational expenditure that we have incurred for subroutine calls, and how we can solve that, one by iteration, second by tail recursion. Okay, so of course not every recursive solution can be converted into a tail recursion. If we can do that, we should always do that, because it will give us a very efficient solution. Now, finally, we are going to look at 2 kind of classic problems just to understand how valuable recursion for problem solving. Okay, so first of all, let's look at a palindrome. Okay, so a palindrome is either a word or a phrase that can be spelled either forward or backward. It will be the same. Okay, so civic, so you can see going from left to right or right to left, same word. Noon, rotor, R-O-T-O-R, from that left to right, R-O-T-O-R, right to left. So never odd or even. Okay, so that's a phrase actually. So left to right or right to left, same. Was it a rat? I saw. So that's even a longer palindrome. Okay, was it a rat I saw? So if you go, was it a rat I saw? Okay, so you can see the space, of course, is at a different place. We are not talking about the space. So if you are forgetting the space, it's the same phrase. Okay. Now, if you are given a phrase or a word or a phrase, okay, and asked to check, is it a palindrome? How would you go about doing it? Okay. So, so first of all, let's consider the input that you get as a string of characters. Okay. So we have to, if we are going for a recursive solution, we have to have the um, base case and the recursive case. Okay. Um, right. So let's first check the base case. Base case. Okay. So if you have a string of just a single letter, like A, for example, okay, it's a palindrome because left, right, or right, left, single letter is a palindrome, right? Not only that, if there is no letter, okay, so we get an empty string. That is also a palindrome because left, right, or right, left, you still have an empty string, a null string, and it's a palindrome. So we can consider as our base case the scenario where we are having either a single letter or no letter, right? So now that we can write as our base case. A string containing exactly 0 or 1 letters is a palindrome. Okay. So this is our base case, which we are formally writing down. Next, we have to get the recursive case. Okay. So when we are checking for recursion of a phrase or a word, what we have to check is whether the first letter in the phrase and the last letter in the phrase, whether they are both the same. They must be same for it to be a palindrome, probably. Okay, because we have checked the other letters also. No? So if it is to be a palindrome, then at that point, the first one and the last one should be the same. Okay, otherwise it's not a palindrome. So we can use this knowledge as a way to build our recursive case. Okay. So what we should do is if the string we have is probably a palindrome, which means the first letter and the last letters are the same, then we strip them off, get the remaining string as the new string, and test it for a palindrome. This is going to give us an increasingly smaller and smaller string to check. And that would be in line with our approach to recursive problem solving. So finally, when you keep on trimming characters from the string, it will either have 0 characters, because if the last one you get is 2 characters, okay, then when you trim left and right, you get null. Or if the last one you get is 3 characters, then you have a single character remaining. Remember, base case takes care of no character, null, or single character. Then the next one is 2 and the next one is 3, like that. So that's how the recursive case will proceed. Okay. So I will leave it as exercise for you to implement the palindrome. Okay, straightforward implementation. Next, so when you are implementing that, make sure that you have a function, you define a function called palindromes, which will allow you to input a set of characters as the input and check, and the answer would be yes or no, basically. Okay. So the answer you return could be 0 if it is palindrome, or 1 if it is not. Okay, you can decide. Now let's look at another problem. Okay, so this another classic problem which is quite often used to illustrate the usefulness of recursion. The usefulness of recursion to give very elegant solutions. So let me first explain the problem. So you have set of 3 pegs, okay, 3 sticks. Let's say they are labeled A, B, C, and you can put discs onto these pegs. Okay, so these flat discs have a hole in the middle, and you can put them into pegs. Okay, And there are n disks you have. Each one has a different size, and we can label it as 1, 2, 3 like that. And 1 would be the smallest, and n would be the largest. Okay, if you have n such disks. So remember, you have 3 pegs A, B, C. So you can think of them as A, B, and C in sequence. And at the start, you have all the disks on the first peg, peg A, stacked in decreasing order towards the top. So it is stacked like this. Okay, the disks. So the bottommost disk would be the n, and the topmost one would be number 1. Okay, label 1. Now this is the starting point. Okay, remember earlier we were discussing about problem solving, and one thing we want to focus is on how to start. Okay, so how to start we discuss. Let's look at what is the data you get. Okay, so here the data you get are the 3 pegs and the n disks and the initial configuration. The disks are on the first peg. Okay, 3 pieces of information: a system with 3 pegs, set of disks which are of varying sizes 1 to n, smallest being 1, largest being n, and the initial condition where all the peg, disks have been put into peg A, which is the first peg. Okay, so that is our start, and we have a goal given. Okay, the goal of Towers of Hanoi problem is to move all the n disks from peg A to peg B, the second peg. But you must do this moving while obeying 2 rules. Okay, so it's like a game with 2 rules. Okay, so at any time you can move only 1 disk. Okay, you can move only 1 disk. And also, so when, okay, remember, when you are moving a disk, you must move it to another peg. Okay, you can't just keep it hanging around. Okay, outside, you must move from one peg to another peg. And when you are doing that, you cannot put a bigger disk on a smaller disk. So it should always be, the smaller disk should be on top of bigger disks. So that's the rule. So here's the graphical representation of the Towers of Hanoi start, okay, and the goal. Now we have to come up with an algorithm, okay, because that's how we solve our problem. Let's consider different cases. Okay, suppose we take the case of a single disk. Okay, that means n equals 1. Okay, in that case we can trivially solve it. Okay, we just move the disk. No, there's a single disk on peg A. We move it to peg B. Okay, so that's the solution, the base case. Okay. So when you think about it, actually, if we have a single disk, we can move that disk to any peg. Okay, so if it is on A, we can move it to B or C. There is no difficulty we will face. Let's consider 2 disk scenario. Okay, so now we have 2 disks labeled 1 and 2. So how can we solve this? Okay, so we have the smallest disk on top and the larger disk on the bottom. Okay, 2 disks. No. So first we can move the disk 1 from peg A to peg C. Okay, so peg C is like a spare peg. Okay, a temporary holding peg. Okay, so we first move the peg, disk 1 from peg A to peg C, and then we move the disk 2, which has now become exposed because now it is the disk that is on peg A, we move it to peg B, okay, which is where we want to go ultimately. Then we move disk 1, which is currently on peg C, to peg B. So that will finish off the task, okay, right? Now, of course, this is similar to the earlier case. We can always move to any peg actually, because of course our goal is to put the disks in peg B. That is why we moved the top disk number 1 to peg C and went like that. But if we have put disk number 1 to peg B, we could have moved the larger disk to peg C and then put the smaller disk on top of that. Okay. Only thing is now the final goal will be achieved not on peg B but on peg C. Now let's take the case of 3 disks. Okay. Now the way we are going to look at this is through recursion. Okay. So we already had a scenario of 2 disks and a single disk. Okay. So now to solve the 3 disk scenario, we have to get the top 2 disks out of the way. So we expose the largest disk 3 at the bottom of peg A, so we can move it to peg B. At that point, peg B should be available, it should be free. Okay, so now we can do this easily by considering the 2 disk scenario. But in the 2 disk scenario, we actually moved from peg A to peg B, but we could have moved from peg A to peg C. So if we do that, okay, if we move disk 1 and 2 from peg A to peg C using B as the spare peg, then once they are on peg C, we can move the larger disk number 3 on peg A to peg B, and thereafter it is straightforward. We can shift the 2 disks on peg C to peg B, because we have all done that kind of thing. Okay, so you can consider peg B as the peg A actually, and the earlier scheme would work. Okay, so you can see now we have looked at how to map our problem into a smaller problem of shifting 2 disks and then filling the moving the larger disk to the goal peg, and then solving the previous problem. Okay. So this way it is just a case of, until we get to the final solution, which peg we consider as the spare peg. Okay, so there will be always a source peg and a destination peg and a spare peg. So the if you look at our original problem, A is the source peg. Initially, all the disks are there. B is the goal peg. Ultimately, all the disks should be there. C is the spare peg. But when solving this problem recursively, we can shift around which one is the source, which one is the destination or the goal, and which one is the spare. Right. So therefore, this approach can be used for any number of disks. Okay, so this will build up a recursive algorithm. So here's the Python code, okay, which will print out a solution. Okay, I'm defining the tower of Hanoi function, and I will tell how many disks are there. Okay, 1, 2, 3, 4, 5, whatever number. And I'm giving 3 pegs, the from peg, to peg, spare peg. So initially, when I call the function initially, of course, n is the total number of disks I have, and first one is the from peg, the source peg, the goal peg is the second one, and the spare peg is the third one, the C, A, B, C. Okay. So if you have a situation of n being only one, so this is the base case. Okay. Then you move the disk one from peg, whatever the from peg, to the to peg. That's what we print. So it's actually the because we are not having a graphical representation of pegs and disk moving between pegs. So we just printing on screen, and we return. Okay, we return after meeting the base case. Otherwise, okay, if n is not equal to 1, what we would do is we would move the top n minus 1 disks. Okay, top n minus 1 disks. So we will act like, let me show you. So we will act like we are only having this set. Okay, 1 to 4, and get it moved to not to this B but to C. In that case, we can move this one here. Okay, so that is how the algorithm will work. So you can see we are now reducing 1. So the bottommost one is kept there, and from peg is where the disks are already placed, and we switch the spare and the to peg. So now the spare peg, the B is the spare peg, goal peg or the destination peg is the the last one. Okay, and we will print this message saying print. So this is so once you have done that, okay, so once you have done that, we can move the disk n from the from peg to the to peg. So the from and to are those that have been there, passed as parameters. Okay, and now we have to return back to the state where the n minus 1 disk which are currently on the spare peg should be put to the to peg, the middle one, and sorry, yeah, there's a typing error here. It should be from peg, which is the temporary peg or the spare peg we have used earlier, which now becomes the source peg. Okay, so when you are looking at this code, always remember this from peg, to peg, spare peg. So this is A, B, C. Okay, A, B, C. And when I first call Tower of Hanoi with n minus 1, this is still A, but this has been switched. A, C, B. Okay, this is A, B, C. This is A, C, B. And afterwards, this will become the spare one. C will become the source. B will become the 2. Anyway, that is the one originally. And the original source peg will become the spare peg. So C, B, A. Okay, let me repeat again. A, I can type it actually so you can easily see it. So this is A, Originally, this is the peg B, and this is peg C. Okay. So I will give you n disk and ask you to move the disks which are currently on A to B using C as the spare peg. When I take n minus 1 peg disks, leaving the biggest one on A to be there, I will go from now A, because that is where the disks are. I will go to the C and using the B as the spare one. And once I have done that, so now all my disks are in the spare peg C. So I want to now move the disks which are on C to B, which is the original goal I have, using now A as the spare one. Okay, I hope it is clear to you. If you implement this in a Python environment and run it, you will see the messages being printed showing how the disk movement will happen. Okay. So moving forward. So now we have completed our discussion on the two classic problems of palindromes and towers of Hanoi. To finish off this particular lecture, I have given two exercises for you to try out. First one is to calculate the sum of list of numbers. Okay, so this is a list of numbers 0, 1, 1, 2 like that, and you should take the sum of these numbers without using a for loop or a while loop. Okay, so essentially you have to do this using recursion. Okay, so the way to solve it is using recursion, no for loops, no while loops. Second one is to solve kind of a classic problem. Okay, interesting. There are 3 missionaries and 3 cannibals, and there is a boat that hold 2 people. Okay, in addition to the boatman. Okay, sorry. So there will be a boatman that is required. The 2 people will at a time can use the boat to cross. Okay, so the rule, so as I discussed earlier, so when you get a problem, you will get some rules also. Yes, the rule is that you will so here's the rule. Okay, if the cannibals outnumber the missionaries on either bank, okay, then there will be a problem. Okay, so what the problem is given here, so you don't want to get to this problem. So this is like towers of Hanoi, but a different type of issue. Okay, so you should do the crossings in such a way at no time on a given bank there are more cannibals than missionaries. So either the number of missionaries and number of cannibals should be the same on a given bank, or there should be only be a missionaries or cannibals on a given bank. Then there is no problem. Suppose on this bank you only have cannibals, yeah, then there's no problem. Or you only have missionaries, then there is no problem. Or you have equal numbers, then there is no problem. But any other situation, will be a problem. Okay, so you have to build your base cases, and then you have to build your recursive cases. So base cases are what you consider to be the solutions for a simplified scenario, and then the recursive case is where you can apply this solution to a smaller problem and get the bigger problem solved. Okay, so that concludes this lecture.